So now we're going to talk about acids and bases. Now the beginning of acids and bases should be very similar to things that you learned in middle school, probably in 6th grade physical science, and or elementary school topics, depending on what level of science your elementary school teacher had the ability of. But now we're going to take it to the high school level, and when we go, if you take AP Chemistry, you'll see a lot more of this. But basically, I'm going to cover about half of everything you need to know about. Everything related to acids and bases. So let's first talk about the definition of an acid and a base. There are two main definitions of acids and bases that we deal with in the honors level. The first one is the Arrhenius, and I always call the Arrhenius the middle school level definition. So an Arrhenius acid is any substance that transfers H plus or has an H plus, basically. Okay, so for example, HCl, HBr, HNO3. Notice that they all have H's in their structure. Now, it doesn't mean just because it has an H, it's going to be an acid. It's just that in the solution, it is transferring that H plus, or it is increasing the concentration of H plus in the solution. Like I said, notice the acid must contain H. Okay, a base is a substance that transfers an OH minus or increases the concentration of OH minus. So again, you're looking for substances that have OH. Notice again that all the substances have to have OH minus in the solution. And this is all by a guy named Arrhenius. So that's the OH minus H plus. Okay, so again, notice that when you're looking at acids, when you look at a chemical reaction, you're looking for things that are moving H plus to be an acid and moving OH minus to be that base. And this is the very, very simple definition of by Arrhenius. Now, later comes along two guys named Bronsted and Lowry. And what Bronsted and Lowry saw were that there was a number of substances that did not fit the Arrhenius definition. For example, NH3, and I'll talk about NH3 in a second. NH3 does not fit the Arrhenius definition of an acid or a base, but ammonia, we know, is a base. So an acid, as defined by Bronsted and Lowry, is any substance that donates a proton. Now, typically, that proton is going to be in the form of H+. So again, you've got HCl, HBr, HC2, H3O2, which, by the way, is acetic acid, meaning vinegar. We'll talk about naming acids in a few minutes. So again, notice that the H plus is going to be a prominent thing again with the Bronsted-Lowry definition. But a base is now nothing more than something that accepts a proton. Okay, so no longer does it have to have OH minus. It can, like NaOH, or it doesn't have to, like NH3. So again, notice that in the case of like NH3, OH is not required to be a base. All you have to do is be able to accept a proton in. So if NH3 can accept that H plus proton from something, then it can be acting like a base. And that's a key phrase too, in a lot of this stuff. It's, does it act like an acid or does it act like a base? It doesn't have to actually be an acid or a base, but if it acts like it, then it's okay. I jumped ahead a little bit and then I'll come back to other stuff later. But how to tell if something is an acid or a base? What I always like to do is I identify where the H plus is and see how it moves. So I always call it follow the bouncing H plus. So I have HCl, which is hydrochloric acid, and NH3, which is ammonia. So I kind of know based on the name which one's the acid and which one's the base, but I'm going to watch to see what happens. So notice that this H here on the HCl moved to the NH3. And I can see that on the product side. Notice that the NH3 is right here on the right, but it has an extra H plus that it didn't have before. And notice the Cl minus is missing its H from before. Had the HCl been the base, then I would see something like H2Cl on the right-hand side instead of HCl on the right-hand side. Okay? Again, notice the NH3 takes in the H+, therefore it is a base according to the Bronsted-Lowry definition, and I can check it. So really that's what's necessary. I cannot look at a substance like NH3 and just like on the page and say, oh, it's a base, unless I absolutely know for a fact that it's a base. Okay? I have to put it into a chemical reaction and see how does it act from the left, the reactant side, to the right, the product side. I can see that the NH3 gained an H+, so therefore it must be a base. Here's another example, okay? So in this example, sodium hydroxide plus HF, hydrogen fluoride, yields NaF to H2O. Which one's the acid and which one's the base? Right. Okay, so I look and I say, okay, well, if NaOH was the acid, it would give up its H plus, forming NaO. But I don't have NaO over here. Okay, so therefore, this H plus must come over and combine with the OH to form this H2O. So this NaOH is my base because it gained an H plus, and HF, which is actually called hydrofluoric acid, is the acid because it gave up the H plus. And again, I have to look from left to right to figure these kind of things out. Okay, so in each of these four reactions, identify the acid and the base. Pause the video, and I'm going to go through the answers in a second. Okay, so HNO3. Let's see. HNO3, if I follow the nitrate to the right-hand side, I notice that the nitrate is missing its H plus. So therefore, this must be the acid. I double-check that the OH here gained the H plus, which it did to form water. So therefore, this must be my base. Okay? So I look at phosphate on the left. Okay, phosphate has hydrogens. Now I look for it on the right. And I say, okay, does the phosphate have hydrogens? No, and it has no extra hydrogens. Therefore, it must have lost its hydrogens, making this the acid and this guy the base. Okay, NH3, H2O. I look at from left to right. Here's the NH3 here. Here's the NH3 here. And I notice that the NH3 now has more hydrogens on the right than it did on the left, which means it gained a hydrogen, which makes it the base, making H2O the acid. Yes, H2O can act like an acid. Last one, KOH. Look at KOH, and I find that, well, here's the K, but it lost OH. It didn't gain any H's. Let me double check the H2CO3. I look for the carbonate. Oh, the carbonate lost all of its H's, so therefore this must be the acid, and this must be my base. The last thing we need to discuss is the concept of strong acids and bases. The term strong refers to any substance that completely dissociates in water. Okay? So strong does not mean dangerous necessarily. Concentrated means dangerous. Okay? If I have a concentrated acid, but it's weak, meaning it doesn't completely dissociate, then it can hurt me much more than a strong acid that's very, very low. It has a very low concentration. Okay? These are your Chevron strong acids. Now, I told you at the beginning of the year that there were only 3 things that you had to memorize all year. 1 was the periodic table. 2 was the polyatomic ions. And 3 are your 7 strong acids and your 7 strong bases. So you have to know your 7 strong acids, which are HI, HBr, HCl, HNO3, HClO3, HClO4, and H2SO4. Okay? So if you look at this reaction, this is a reaction involving hydrochloric acid. And hydrochloric acid dissociates into H plus and Cl minus. So when it's in solution, HCl doesn't actually act like HCl. It acts like H pluses and Cl minuses, totally separate from each other. Bases will do something very similar. So bases, you have sodium hydroxide, lithium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide as your 7 strong bases. Again, you need to memorize these. Okay? So basically, whenever any of these 7 strong acids are in a reaction, think just H plus. You don't even care about the other ion because the other ion is unimportant. When these 7 strong bases occur, the same kind of thing. We only care about the OH minus. We don't care about anything else because the other stuff is inconsequential to the actual reaction. Okay, now let's name our acids. Now, there's no topic about bases. There's no naming of bases. And the reason we don't need to name bases are just named the same way you would name a compound. So like NaOH is sodium hydroxide. So you take, it's ionic. So you just take its 2 ion names and you add them together and boom, you've got the name of your strong base. Okay? But acids are a little bit different because the hydrogen being present actually affects the name. So there are 3 types of acids that we're going to name. The first one is if the anion ends in IDE, like chloride, bromide, fluoride, etc., then what you do is the name starts with hydro and ends with ic acid. For example, hydrogen chloride becomes hydrochloric acid. Okay, so Cl is chloride, so we turn that into ic acid, and we put hydro out on the front, so it becomes hydrochloric acid. Hi would be hydroiodic acid. HF, hydrofluoric acid, etc. Number 2. Now, these are the two that cause people problems, are your acids that involve oxygen. If your anion, your negative ion, ends in ITE, like sulfite, nitrite, phosphite, etc., remove the ending and add OUS acid to the end of the ion. For example, SO3 is sulfite, so it becomes sulfurous acid. No hydro. Okay, so just sulfurous acid. So the ite becomes OUS acid. And the opposite one would be the ates. Okay, so if the anion ends in ATE, you're going to remove the ending and add ic acid to the end. So HNO3 becomes nitric acid because NO3 is nitrate, so the nitrate becomes nitric acid. Again, no hydro. The hydro tells you that it's what's called a binary acid, meaning there are only 2 atoms in the actual molecule. Okay? Or 2 types of atoms. Okay, so now I want you to name the following acids and bases. Pause the video, go through them, and double check your answers, and I'll write them down in a second. Okay, so HBr. Br is bromide, and it's got a hydrogen, it's an acid, so this must be hydrobromic acid. HClO4. Well, ClO4 is perchlorate. It's got ends in ATE, so this must be perchloric acid. HC2H3O2. Well, this part is acetate, so this must be acetic acid. Phosphoric acid. Well, phosphoric refers to phosphate, so it must be PO4 with a 3-. It's got to have hydrogen, so it must be H3PO4. Carbonic acid. Carbonate is CO3, so this is H2CO3. Now my bases. Bases are super easy. NaOH, sodium hydroxide. Oops, no extra dot. CaOH2, calcium hydroxide. And last, strontium hydroxide is Sr, and Sr has a 2+ charge, so it gets 2 hydroxides. SrOH2. And that's strontium. And that's everything you know about the introduction to acids and bases, naming, and how to identify them in chemical reactions.